Hi everyone. I just want to briefly finish up this chapter by giving a little lecture on matroids and greedy algorithms. So the whole reason we introduced matroids was because we've seen a lot of different examples. So we've seen vector spaces, we've been talking about linear algebra in this course. We've been talking about graph theory, and we've been talking about rigidity theory. And we've noticed, right, commonalities between those three subjects. Like there are linearly independent sets of vectors. There are sets of edges in a graph that don't have any cycles. Those are kind of independent. And then we know that there are independent sets of edges in a framework, okay? And the language of matroids lets us sort of, in an abstract kind of high-level way, help us to see the commonalities between those three things and the different properties they satisfy, right? That in each realm, in each category, there are bases and independent sets and circuits. And one of the things you can do when you have a matroid is you can construct a basis greedily. And that's what I want to talk about here. So what would a greedy algorithm for constructing a basis of a matroid look like? Well, the input to this algorithm is going to be the matroid, okay? And the output should be a basis for the matroid. And what are you going to do? Well, you can say, okay, compute the rank of the matroid. See, that's known because you have the list of all the independent sets, and you can just look and see like what's the cardinality of the largest independent set. Okay, that's the rank. And then the way the algorithm proceeds is really simple. It sets B to be the empty set at the beginning. And you just need an arbitrary ordering on the elements of E, the ground set. And then starting with the first element in the ground set, ask the question, is the set B union EI independent? If it is, then update the set B by inserting EI into it. And then, if the cardinality of this new set B is still less than the rank, try step 4 again. And then you're going to keep looping around until eventually you get a set that has size equal to the cardinality of R, and then you'll stop and output B. So before we show why this, say a few words about why this works, let's look at an example. So suppose we wanted to build a spanning tree. So let's say we have the graph G, where it's going to be, suppose we take edge 1, edge 2, edge 3. We're putting an ordering on the edges here. And then, this is, I guess, the bow tie graph. Edge 4, edge 5, edge 6. Okay. So suppose this graph essentially is, or the edge set of this graph is the input to your to the greedy algorithm together with all the independent sets. And then we're going to construct a basis for this greedily. So what would the greedy algorithm do? Let's just assume that the ordering on the edges is the one I've just given. So the edges are ordered E1, E2, E3, E4, E5, oops, E6. And what the algorithm does is first, it sort of says, let's let B equal the empty set. And then we're going to look and we're going to say, is the empty set union, I'm going to use the plus notation, is the empty set plus E1 independent? Yes. So then we're going to say B is equal to the empty set plus E1. So then it's E1. Okay. So then we're going to loop around again and say, well, let's consider the second edge, E2. So far, let me put this in blue maybe. We've got this in our basis, our independent set, the basis that we're trying to grow. And then we look and we see, and we ask, is E1 plus E2 independent? Well, when we look at the graph, yes, it is. So we'll throw that in there. And now in our updated B, B is equal to E1, E2. Now we ask for the third edge, is B plus E3 independent? And the answer is no. So we just don't do anything. We go to the next one and we say, is B plus E4 independent? And in fact, it is, because it doesn't create a cycle. And then, so we know that what's the rank? The rank of the matroid. So since G is a connected graph, spanning tree for G is going to have one fewer edge than the number of vertices, and there are 1, 2, 3, 4, 5 vertices. So I should be looking for 4 edges. Okay, so now I have B equal to E1, E2, E4. And then finally, I ask, is B plus E5 independent? It is. So the algorithm would throw the edge E5 into the graph. And so we could say, oops, B equals B plus E5. And now B has 4 elements equal to the rank R. And so we want to output the basis B. I guess I'll just write output B, which is E1, E2, E4, E5. Okay? So I just want to say a few words about why this works. And fundamentally, why this works is due to the theorem that we proved. A couple theorems, right? So one important point is that we proved that every independent set is contained in some basis. Okay, so that means as we start with an independent set, we start with the empty set, and as long as we keep adding elements in that are, and we sort of maintain an independent set, that set can be grown to a basis. I guess we also have to know that eventually this is going to stop. So we may know our matroid has a basis. We know every independent set is contained in a basis, and we know we have finitely many elements, so that to try, right, to test, so that it has to stop, because we can't go on forever, and eventually we will get an independent set that has rank R, that has size R. Okay, so it eventually stops. Of course, the key point is, can you really check for independence quickly, right? So in linear algebra, you might do that linear independence check by putting your vectors in a matrix and doing some row reduction. And then you have to think, like, how would you do it in graph theory? And in particular, how are you going to do it for rigidity theory? And in rigidity theory, what we're gonna see in the next chapter, that there's a really nice fast algorithm called the Pebble game algorithm, and it's gonna be really cool. All right, I'll stop here.